Okay, so we're going to look at concave mirrors, and we're going to look at when the image is between the focal point and the mirror. So we have our concave mirror. It's actually a mirror built within a circle, and there would be the center of the circle, the center of the concave mirror, and the focal point is halfway between the mirror and the center, according to our first formula. So we're going to remove our circle here and delete it, just so it looks a little more like the mirror would be used to looking at. And in this case, we're going to have an image that is between the focal point and the mirror. So I'm going to put our image here, okay, which means the object itself has a distance of 2 units. So the distance of the object is 2 units from the mirror. Okay, and we'll say the height of the object, HO, is 1 unit. Now I guess we should go through our formulas here just to make sure. Our second formula is 1 over the focal point is equal to 1 over the distance of the object plus 1 over the distance of the image. The magnification is equal to the height of the image over the height of the object, which is equal to negative the distance of the image over the distance of the object. If you don't know what each of these variables stand for, you can pause here and go through and take a look at each of them. Okay? And if not, you need to pause here, look at the formulas, you can take a look at that. Okay, so we have our stuff that is defined. And with that, we know the focal point, since the center is at 6 for our very first formula. The center is 6, therefore 2 times the focal point. The focal point is at the distance of 3. Okay, so let's kind of delve into our formulas to try to figure out where our image would be. So 1 over the focal point we said was 3, is equal to 1 over the distance of the object. The distance of the object is 2, plus 1 over the distance of the image, and the distance of the image is unknown. So we need to isolate for distance of the image. We bring over a half, so we get 1/3, subtract 1/2, and we're going to need a common denominator in order to subtract these. So the quickest way to do this is to multiply one fraction by the opposite fraction's denominator. So we multiply both of these by 2, because that's the opposite denominator. And then in this fraction we multiply both top and bottom by 3, because that's the opposite denominator. So we get 2 over 6, subtract 3 over 6 is equal to 1 over the distance of the image. Now, that will give us actually negative 1/6, which is equal to 1 over the distance of the image. Now we can just flip the fractions, or we can cross multiply, whatever is easiest for you to understand. I think I flipped them in another example, so I'll cross multiply in this one. Distance of the image times negative 1 is negative distance of the image, and 6 times 1 is 6. And in order to get a positive value of the distance of the image, I need to divide both sides by negative 1. Think of it like that. So, it's good to know we don't have milk there. Distance of the image is negative 6. Okay. So now with that value, distance of the image being negative 6, we can go into our third formula. Our third formula stating that the magnification is equal to the height of the image over the height of the object, which is equal to negative the distance of the image over the distance of the object. So if we want to just find the magnification, we really only need to set one set of these equal to the magnification. And since we don't have any of we don't have the 2 pieces of info here, we'll set this one equal to the magnification. We just figured out that the distance of the image is negative 6. So that means we get negative 6 over distance of the object. And if you remember, the distance of the object was 2 units. So over 2 is equal to the magnification. So the magnification is equal to, that becomes positive 6 over 2, which is positive 3. Okay. So with that being said, let's set these ones also equal. The height of the image is unknown, but the height of the object we knew to be the value of 1, which is equal to, again, negative 6 over our value of 2. This side gives us 3. We already solved that over here. And the height of the image divided by 1 is just the height of the image. So the height of the image is 3. Okay, so we have this information. So what we now need to figure out is how to apply this, with our rays. So we have our image. So our light rays here. Our first one goes to the mirror and then back through the focal point. Okay. While our next one, okay, and this is similar to when the image is, or the object is at the focal point, goes to the primary axis of the mirror, and it actually diverts away, comes off at an equal angle. Let's try my best to make this the equal angle. I think that's roughly it. Is that it? I'd say that's roughly the angle. Okay. So you can see that these are actually diverging. They're getting farther and farther from each other. So what we can do, though, is follow these backwards. And if we follow them backwards behind our mirror, let's try our best to run this here. Well, it looks like we're going to start to find our image somewhere behind the mirror. So let's go to our numbers to see if I've kind of drawn this correctly. The magnification was positive 3, the height of the image was 3, and the distance of the image, that's what I was looking for, was negative 6. So we're looking at negative 6, okay? So that's here. This is the negative 6. This is where the image is going to show up. So we'll do the image in red. Okay, it's at negative 6. And it said it had a height of 3 because it's being magnified by a case of 3. So my lines are not bad. They're almost there. A little more like this, I think, is the case. Okay, and where they two diverge is where our image is. It looks like it's behind the mirror. This has a height of 3. So because this was a height of 1, we multiplied it by 3. We got our height of 3. And our image is negative 6 behind the mirror. So mathematically, this all also worked out with all of our values. So that's when the image is between the focal point and the mirror.